First, thinking about this problem qualitatively, we have a positive proton and a negative electron. So opposite charges, they should be attracting. Notice that we are also given the actual quantity of charge, the positive 1.6 times 10 to the negative 19th and the negative 1.6 times 10 to the negative 19th coulombs. This number is known as the elementary charge, and if it's ever not given in a problem, it is listed in your data booklet. So now thinking of this problem quantitatively and using Coulomb's law, F equals KQQ over R squared, we start to plug in. We have F equals K. K is, of course, 8.99 times 10 to the 9th, as listed in your data booklet. Q1 and Q2, it does not matter which one you list, first or second. So positive 1.6 times 10 to the negative 19th, negative 1.6 times 10 to the negative 19th, divided by the distance between them, or 2 meters squared. Now, as you're typing this into your calculator, there are a lot of exponents. There's a lot of scientific notation, so be very careful when typing it in. Another very common mistake is when typing it into your calculator, you need to put the entire numerator in parentheses and then divide by that 2 squared. So in the end, you should get about negative 5.8 times 10 to the negative 29th newtons. If you are not getting this number as your answer, go back and do a double check in your calculator. Are there parentheses around the numerator? And are you dividing that numerator by 2 squared? Don't forget that squared. Now you'll notice this is not very much force, negative 5.8 times 10 to the negative 29th. So that's 0.00029 zeros, 58 newtons. Not much at all. Let's move on to problem number 2. This problem, very similar, except now we're asked to find the force that one electron and another electron exert on each other when placed at 2 meters apart. Take a moment, pause the video, and first think about this qualitatively. Do these charges attract or repel? Now think about it quantitatively. Thinking about an electron and an electron, these are like charges. So qualitatively, we automatically expect that these charges should repel one another. Thinking about this quantitatively using Coulomb's law, we have the force is equal to K, 8.99 times 10 to the 9th. Again, this is Coulomb's constant as found in your data booklet. We have Q1 and Q2. Here they happen to be the same because we're talking about 2 electrons. And notice that I'm carrying that negative through. Divided by R squared, the distance between them squared, here is 2 squared, or 2 meters squared. As you're typing it into your calculator, be very careful with those exponents, that scientific notation. Make sure that you're putting your numerator in parentheses before dividing by that 2 squared. And of course, don't forget that squared. You should be getting a positive 5.8 times 10 to the negative 29th newtons. You'll notice the magnitude is the same as in the previous problem, but here we're getting a positive because that negative and the negative of our Q's are multiplying together to give us that positive. Again, not much force, very, very small amount. Our last problem is going to ask us what is the force that one proton and another proton would exert on each other when placed 2 meters apart. Very similar to the previous problems. First, think qualitatively, will these charges attract or repel? And then solve quantitatively. Pause the video and give this a try. Thinking about a proton and a proton, these are like charges, so we expect that like charges would repel one another. Quantitatively, using Coulomb's law, we can start to plug in that the force is equal to K, our Coulomb's constant, 8.99 times 10 to the 9th, times our first Q and our second Q. Here they're both just the Q of a proton, the charge of a proton, 1.6 times 10 to the negative 19th coulombs. Notice that I've kept those positive signs in there. Divided by the distance between our charges, or 2 meters squared. Similar to the previous problems, you should be getting a final answer of positive 5.8 times 10 to the negative 29th newtons of force. Again, we're getting a positive in this question because we're multiplying a positive charge times a positive charge. This brings me to the sign of the force that we're getting. You'll notice that the first question we got a negative force, and the second and third examples we got positive forces. So knowing that opposite charges will attract and like charges will repel, let's think about what is the sign of the force when charges attract? What is the sign of the force when charges repel? Take a moment to record your thoughts on your paper. If you said that an attractive force would be negative, you would be correct. Of course, this negative is coming from opposite charges, so maybe Q1 is a negative charge and Q2 is a positive charge. Negative times a positive would give a negative force. Or maybe it's flipped around that Q1 is a positive and Q2 is a negative, still, when multiplied together, giving us a negative force. And if you said a repulsive force would be positive, you would also be correct. So Q1 and Q2 being like charges, so either a negative times a negative would result in a positive force, or a positive times a positive would result in a positive force. So when using Coulomb's law, don't forget about those signs. A positive and a negative force really express a direction, a repulsive or an attractive force being felt by charges. Very important part. And that concludes the lecture. When you get to class, you're going to be putting what you learned in this lecture into practice by looking at some real-world examples. So on your guided notes, if you take a moment to summarize and reflect on this lecture, you will be ready to go.